Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today, our lesson deals with chemical bonding and the following concepts are described. The octet rule, ionic bonding, Bohr-Rutherford diagrams for positive ions, Bohr-Rutherford diagrams for negative ions, Lewis dot structures for ionic compound, and it starts on page 42 and ends on page 50 from the text Chemistry 11 in Focus. What will life be without the various types of chemical bonding? From the simplest of molecules to the most complex ones, bonding is essential. Molecules of proteins, fats, and carbohydrates, for example, along with water and vitamins, are critically involved in building and maintaining bodily structures and in carrying out various metabolic processes in living organisms. These molecules are all held by special types of bonding. The replication of the DNA molecule is made possible because of the weak hydrogen bonding that exists between its two strands that can easily break and reform. Water is a liquid at room temperature because of the intermolecular forces between its molecules. In our non-living world, all structural entities, natural or man-made, are maintained by some type of bonding. The softness of graphite to the remarkable hardness of diamond is attributed to the difference in which the carbon atoms are naturally bonded within these two substances. The softness to the firmness of our foam mattresses is achieved by deliberately manipulating the type of bonding within them. The same can be said of the nature of adhesives that are made to bond firmly to specific substrates, or of fast-setting dental paste and alginates. Everyday marvelous compounds are created for household and industrial uses. These include the drugs in the medicines we use, to the compounds needed to make concrete roads, building, bridges, aircrafts, and countless other man-made structures around us. Without bonding to hold atoms and molecules together, everything, including our bodies, will spontaneously break apart into their respective atoms. Whoa. It is therefore important to study how bonding takes place, such that we become more aware of the naturally occurring compounds and their potential uses in society and living organisms, and also to create newer, more beneficial ones. What I'm going to show you first here are the Bohr-Rutherford diagrams for the first four inert gases in the periodic table. Here is helium, neon, argon, and krypton. If you look for certain patterns, what patterns do you see there? What is common in these four atoms here? If you say they all have 8 electrons in their valence shell, the outer shell is called a valence shell, you're correct. They all have this octet. This arrangement where you have 8 electrons in the valence shell of an atom is called the octet arrangement. And in the case of helium here, you're having 2 only, it is called the duplex. So what makes these guys peculiar is that they are non-reactive. And scientists have attributed that inertness to this arrangement of 8 electrons in the valence shell, the octet, and the duplex arrangement here. Other elements of the periodic table now do not have this arrangement, and they would like to gain the stability of these elements here. So what they will do, depending on the number of electrons they have in their valence shell, to achieve that octet or duplex arrangement, they do one of three things. They'll either gain electrons, they'll lose electrons, or they will share electrons. We won't be studying this one now because that is involved in forming covalent bond. We are doing ionic bond today, so we only be looking at elements that gain or lose electrons to achieve the inert gas electron configuration. I'm going to show you part of a periodic table, and we want you to see the number of valence electrons in each of these here. But I just quickly want to review for you something called electron configuration. Be reminded that in the first shell you only have 2 electrons because it can only hold 2. The second shell can hold 8 electrons. The third shell can hold 8 electrons. And the other one here, whatever is left goes here. So let us say that you have an element like lithium here, right? How do you do this electron configuration? You take out 2 of these electrons here, and you fill that shell here, so 2. What is left over now goes into the other shell here. However, if the number of electrons left over is greater than 8, then you have to complete this 8 here. Let's look at sodium, for example. Sodium has 11 electrons. So 2 will go into the first one. When you do the math, you're left with 9 left over, right? So now you have 9, you complete this one here, get 8, and the other one is left there. If the atom gets bigger than that, let's say calcium, for example. Look, calcium has 20 electrons, okay? You put 2 in the first one, so that leaves us at 18. Complete the other one with 8, that leaves us with 10. And the other 2 go here. We also show the electron configurations for the noble gases, because we want to make comparisons between these and those. Now, I want you also to look at some trends in the periodic table as we here. Notice how lithium has 3 electrons and that has 4, 5, 6. So as you move through a period from left to right, the number of electrons increases by 1. Okay? You can see here, if you start with the first one, all you do is to keep adding on to the next one and you get the number of electrons there, okay? And you can see here, the number of electrons in the valence shell will increase also by 1 here. So you move that, it increases by 1. Number 2, down a group, see what is happening down a group. As you go down a group, you alluded to this already, the number of valence shell increases by 1. So this has 2 valence shell, this one increases by 1. And when that happens, it's adding 8 more electrons to the atom. So the atom gains 8 more electrons. So sodium will have 8 more electrons than lithium because of this extra full shell here. As you go downwards a little bit more, you have another shell that has 8 electrons, so increases by 8. So as you go down a group, the number of valence shell increases by 1, and so does the number of electrons. You have 3, 11, 19. So these are some trends I want you to see. Most importantly, we said that atoms of elements will try to gain an electron configuration of an inert gas that it most closely resembles. Now lithium here has 2 and 1, so it most closely resembles this one here. See that? So you try to gain an electron configuration like this. So it has a duplex here. Lithium does have the duplex, but it has an extra electron. So the obvious thing will be for lithium to shed this electron, and when it does that, it becomes like this. Here, beryllium is 2. It'll do the same thing. Give away 2 electrons to become like that. Boron, 3, like that. But this group is a funny group here. We'll talk about this later on. See, you see carbon? Carbon can do one of 2 things. It can lose these 4 here to become like that, or it can gain 4 more to become like this guy here. It does neither of that unless it is really reacting with an element that can really push electron onto it or remove the electron. In most cases, it doesn't do that, but it is involved in something called sharing of electrons that we'll do later on. Now, if you look at the pattern here, look at this group here. Within the group, what are you noticing about the valence electrons? They have the same number of valence electrons. So group 1A, each atom has 1 electron. Group 2A will have 2 electrons in the valence shell. Group 3A, 3 electrons. So looking at this here, you can actually tell how many electrons will be lost depending on which group the elements are. So that's why I always implore my students to learn the first 20 elements of the periodic table, know which rows they are in, and know which groups they are in. And from that, you can know so many other different things about them. What happens when lithium loses that 1 electron to become like helium? So this is the 1 electron here. Lithium loses the 1 electron and is left with the duplex here. Mind you that they all have, this has a duplex, this has the octet, it has the octet here. In the penultimate shell, the one just before the last shell. So to remain with the octet, these will lose these electrons here. So this one loses an electron here, and look what happens. It becomes a positive ion here. Sodium loses 1, gains the octet here, becomes a positive ion, 1 positive, so does potassium here. And in the end, they all have the inert gas electron configuration. Look at group 2A. It's losing 2 electrons and is becoming 2+. Look at the relationship between the number of electrons lost and the charge that is getting. By the way, this charge that is acquired here is called a valence. So group 1 will have a valence of 1. All group 1 atoms, when they lose the electron, these are called the ions. The ions will have a valence of 1+. Don't put +1. That's not correct. That's when you describe its oxidation state. Always put a number before the sign there. So group 2, all of them, because they're losing 2 electrons, they'll all remain with a valence of 2 positive there. So if you remember group 2 elements, right away you know they'll have a charge of 2 positive. Group 3A, because they have 3 electrons, they lose the electrons, they get the inert gas configuration, and they acquire a valence of 3 positive. Groups 1A, 2A, and 3A, they'll all lose electrons to acquire the inert gas configuration whenever they react. These elements that lose electrons are called electropositive elements. Now we come to another set of elements here. So we talk about this guy a little bit. Only if a very electropositive element is reactive, it can force the electron onto it. It can become negative. That's in the case of calcium carbide, for example. It's an ionic compound and some type of exchange took place there. We're going to look now at group 5A, group 6A, group 7A, and of course, we're putting inert gases there for us to compare. Now look what is happening, and these are now non-metals. Electropositive elements, like the one we described just now, are all metals. These electronegative atoms are the ones that will gain electrons, and they are non-metals in this case. Nitrogen has 5 electrons in its valence shell, so does phosphorus. Nitrogen will gain 3 electrons to become like this. It will be easier for it to gain 3 electrons to become like this than to lose 5 electrons and remain with 2. Same thing for phosphorus here. So group 5A elements of the periodic table will acquire 3 electrons each. Now this one has 6, so does this one. So the obvious thing for this to do is to take 2 electrons to be like that. Sulfur will gain 2 electrons to become like this one that it most closely resembles, right? These one will give 1 electron each to become like that, all right? Same thing for bromine here. So elements from group 5A, 6A, and 7A will gain electrons to acquire the inert gas electron configuration. Okay? And of course, you know the groups here. You know how many electrons each they will gain. Now, let's see what happens when they gain these electrons, like we did for the other one. Now, look. When this one gains 3 electrons, it acquires a valence of 3 negative. So here again, you're seeing a relationship between the number of electrons gained and the charge that appears on the ion here. So group 5A will gain 3 electrons, and each of them will gain a valence of 3 negative. Group 6, 2 electrons, 2 negative, 2 electrons, 2 negative. Again, relationship between number of electron gain and the valence here. Group 7 now, that's 7 electrons outside. They only need 1 more, and see what happens there. Each of these will acquire a charge of 1 negative. They'll have a valence of 1 negative. Okay, now we'll go on to see why they acquire these charges, when they lose electrons and when they gain electrons. So note the trend then. Bohr-Rutherford diagrams for positive ions. We'll use this to represent what happens when any other positive ion is formed. This is the Bohr-Rutherford diagram for the sodium atom. Here you can see 1 electron is in its valence shell. Therefore, it wants to lose that 1 electron to remain with the octet here. So you got your 1 electron given off there. See how this shell disappears? But it acquires a positive charge. Why does that happen? Now you must know something about every atom. I've spoken about that already. Every atom is electrically neutral. That's because the number of protons is equal to the number of electrons. Each proton carries a positive charge. So 11 protons is here. You'll have 11 positive charges. 11 electrons, 11 negative charge. When you sum these up together, they'll neutralize each other, so you have 0. Because this guy is losing an electron, it's not with the atom anymore. Let's see what's left in the ion. Note that protons do not move. Protons are stuck in the nucleus of the atom. Only electrons, valence electrons are either coming in or going out. Okay? In this case, an electron went out. We had 11, now we have 10. So you can see there's a disbalance in the charge here now. You have an extra proton when compared to electron, and therefore because of that extra proton, it acquires a positive charge. Same thing will apply. If it had lost 2 electrons, this would have been 9, and then it would acquire 2 positive charge. Like what happened, that is what is going to happen in group 2A. Magnesium, calcium, and beryllium and stuff like that. If it had lost 3 electrons, then it would have remained with 3 extra protons, as happened in group 3. Okay, with boron and aluminum, it would have acquired a charge of 3 positive. So I'll give them to do some of that. That's from the book there. Let us see what happens for negative ions. Why does chlorine become negative? Same concept. Now, 7 electrons here in the octet, so this one will acquire an electron. So it acquires an electron. Know how it blows up a little bit here because of more electron repulsion here, and it gets a negative charge. Why does it gain a negative charge? Similar analysis. Neutral before, 17 electrons, 17 protons, 0 net charge. But because now it is gaining an extra electron, see? You'll have 17 positive charges due to the protons and 18 negative charges due to the electrons. And you can see number of electrons is greater than protons, so the net charge on the ion will be 1 negative. If you're doing group 6 elements, say oxygen or sulfur, they would have acquired 2 extra electrons and would have made their ion 2 negative. Bohr-Rutherford diagrams for ionic compounds. Let's see what happens if you were to react sodium and oxygen. Look at this diagram here. You start with neutral atoms. This is the Bohr-Rutherford diagram for a sodium atom. And this is the Bohr-Rutherford diagram for another sodium atom. This is the Bohr-Rutherford diagram for oxygen atom. Now when we analyze this oxygen atom here, you see it has only 6 electrons. And this has 1 electron here and the 1 electron here. This is an electropositive element, and it would like to lose electrons. Same thing here. This can lose 1 electron when it reacts. But oxygen, being electronegative, requires 2 electrons to gain the octet. This sodium can only donate 1 electron here, and therefore oxygen would not have had its octet. It would have had 7. So you need another sodium. That's why we're using another sodium to put that other electron here onto the oxygen. So in the end, this one would have lost one electron, sorry about the dissociation, and this one the same thing, but this would have acquired 2 electrons. So the net result is you're having an oxygen ion that's slightly bigger with 2 negative charges, and each sodium here remaining in 1 positive charge. One thing I want you to know is this. When an ionic compound is formed, it is neutral. This is true because the sum of the charges on the positive ion is equal to the sum of the charges on the negative ion. And this is what happens in any ionic compound. In this case, oxygen is carrying a 2 negative charge, the ion, and each of these has 1 positive. When you sum them all together, the number of charges are equal and opposite to each other. If one were to ask you now to write the formula for the reaction between sodium and oxygen, here you're seeing you're using 2 sodium and 1 oxygen. That is why when you write the formula now, it's going to be Na2O. Okay? The same strategies are used to draw the Bohr-Rutherford diagrams for the reaction between atoms of different elements. So they want you to do between this one and this one. It'll be 1 to 1. It'll be LIF. Magnesium and chlorine, you have to figure all this out, how many electron one is given, how many the other one is taken, and then you figure out what ratio of atoms you must use. Now we're going to do electrostatic force of attraction and the ionic bond. I've spoken about this when we did electron affinity. If you bring a negative charge in the vicinity of a positive charge, see, every positive charge has an electric field with field lines coming out of it, and then negative charge and electric field lines coming into it. If you bring these two close together, these field lines will link and they will contract, causing the two charges to attract each other. Same thing that will happen when an ionic bond is formed. If I have sodium ion and a chloride ion, the same thing is happening. Electric field lines are going out from that one and it's coming into this one. They link, they contract, and because of this force of attraction here, it is called an ionic bond. These are full-fledged positive and negative charges, and they are ions. That is called an ionic bond that is relatively strong. Now we will do electron dot diagram for ionic compounds. G. N. Lewis, 1875 to 1946, used the valence electrons of reacting atoms to show how electrons are lost and gained in the formation of ionic compounds. If I were to ask you to draw the Bohr-Rutherford diagram to show how potassium reacts with fluorine, one would have had to do as was done for the reaction between sodium and oxygen previously. But Lewis has given us a shortcut. Instead of doing all of that, he said, look, just use the valence electron here. We know potassium is in group 1A. It has 1 valence electron. Fluorine is in group 7A. And we know all of those have 7 electrons. We know that this needs only 1 more electron to acquire the octet. And therefore, this potassium is a willing donor here. And it's a 1-to-1 ratio here. So we show how that electron comes here. So you will end up now with a fluoride ion, and the fluoride ion will show the octet here. And of course, because there's a kept in 1 electron, it will have 1 electron more than protons, and will gain a charge of 1 negative. Here, potassium is losing 1 electron, and will have an extra proton than electrons because of that 1 loss, and it will acquire positive 1. Note how the octet is only shown for the negative ion and not the positive ion. Not to say that this doesn't have the octet. The octet is inside of it. The penultimate shell has the octet, but this is an understanding what we have. We only show the octet on the negative ion here. So this we call KF. Look again, 1-to-1. 1-to-1. See that? Because this is 1 negative, 1 positive, and that's how it happens. So it makes sense. If one were to ask you to do this without doing the Bohr-Rutherford diagram, then it wouldn't make sense to you. That is why it's important that you do a few of the Bohr-Rutherford diagrams to show how the electrons are moved from the metals to the non-metals, and then you understand how they acquire the charges and how the formula ensues from that. then this will make sense. Okay? All right, let's move on now. See what is happening. Do another one. This is exactly the one that we did before. We did the Bohr-Rutherford diagram for this one. So this is a shortcut. See, oxygen needs 2 electrons to make the octet. So this is a single sodium atom, a single sodium atom with its valence electron here. One from that, one from that. It requires 2. We show the octet here, 2 negative charge. Then each of these will carry their own 1 positive, own 1 positive. And again, you write the formula like that, Na2O. Okay? And we can do other examples. Look, in this case now, we're using a metal that is given 2 electrons. This is given 2 electrons, but each chlorine is only capable of accepting 1. You have 7. So for 1 magnesium to react, you need 2 chlorine atoms to react with it. So it gives 1 to that one, 1 to that one. Now it is left with 2 less electrons. It acquires a positive charge of 2 plus. And each of these is acquiring 1 electron. And again, an extra one there. And that manifests itself as a negative charge here. Look how you write the formula. 1 magnesium with 2 of these at the side there. Lucky guy, see? Magnesium chloride is like a king with 2 princesses, you know? Queens. So that is it, magnesium chloride. So that's it.